Hello guys, good evening, afternoon or morning, alright? So today will be like a extra tutorial on differentiation, right? And let me just write that down real quick, yeah? So the differentiation, right? And what is the definition of differentiation actually, alright? It's basically the act of taking a derivative at a point of a function that is graphed out, that is plotted into a graph, or map or graphed out, whatever you want to put it, so this is like a very simplistic non-rigorous definition of differentiation, right? A very easy way to understand it, and we know that it's related to a derivative, and it's of a function, well, at a specific point of a function, really. So in order to understand it more, we need to really understand what is a derivative. So the derivative actually is the rate, of change of a function, we can represent it fx at a point x, at a point x. So let me actually just sketch a simple function right here, right? If we draw the axis, so x, y. Alright, so let me just draw this here real quick. So let's pretend this is our function right here, it's something like this, and we're interested in this point A, I'm gonna put a plot here, point here. At this point A, right, that we're interested in, we'd want to find what's the derivative of A, right? We want to know what the derivative is. So one way to do this is to plot another point right here, and we're gonna denote it as A plus delta x, and if I were to connect a line between these 2 points, a nice straight line right here, it's almost straight, cool, right? So this line touches between A and A plus delta x, and we can see that the change from this particular point right here, A, to A plus delta x in the horizontal direction is just delta x, right? But how about in the vertical direction, the y direction? It's basically the difference between y1 and y2, so what is y1 and what is y2? So y1 actually is related to A, whereas y2 is related to A plus delta x, right? So why I'm trying to bring this point up here is that for this particular line that we just draw, we can find its gradient, which represents the rate of change, by the way, is simply y2 minus y1 over delta x, right? And if I write it more precisely, it would be something like this: f a plus delta x, that's your y2, minus f a over delta x, so that is your gradient of the line itself, which is also our derivative, and if that particular delta x, as the limit of delta x, as we learned earlier, right, approaches to 0, and f of a plus delta x minus f of a itself over delta x, as it starts to converge or get very, very small, eventually, okay, I'm going to highlight this in green. Eventually the line will be here. Oh, actually no, sorry, it'll be somewhere like this. Okay, eventually it will be somewhere like this. It will touch A, but it will not touch the other points in the graph itself. Okay, so it would be considered like a tangential line. Okay, of course, you know, it won't reach zero, because of course if this reaches zero, then this whole entire thing will become infinity, right? Which is obviously not the case right here. So yeah, eventually you'll come to a point where you'll be able to find the derivative of a itself, actually, right, as delta x starts to approach zero. So that's basically the concept or the idea of derivative itself. Okay, like how is it originated from? Okay, and one use of derivatives normally is to find the gradient at a particular point. Okay, so if you find the gradient at any point of a graph, okay, of a graph, all right. And this is a lot of real world uses, actually, because for instance, if we are plotting a distance time graph, by the way, so you're plotting a distance versus time graph, okay, the gradient of the graph is velocity or speed in this case. So gradient will obviously represent the speed at that point, at a point. Okay, let me just erase that. Yeah, at a point. Okay, so at a point itself. All right. Because in a distance time graph, okay, let me just erase this real quick. Okay, let me just make this a bit bigger. Erase this eraser real quick. All right. So, oops, sorry. This part only. I'm gonna erase it real quick. Yeah. Okay. Cool. So, for speed at the point, because we know a distance time graph is definitely a graph where it would be something like t in the horizontal axis and x in the vertical axis, right? And if you were to draw a distance time graph like this, for instance, okay, let's just pretend it's like this, and at this point I'm gonna mark it in green. Okay, let's say we want to find it we want to know what's the speed at a point of when t is 2 seconds, for example, right? So we want to know what's the speed. Right? We only got the distance x and we only got the time t. So we know that if we were to divide the distance by the time, okay, or the change of distance with change of time, automatically you'll get the speed, right? So that's where you can say that the speed at 2 seconds is basically the gradient at 2 seconds, right? We should draw the line right here. So that's why finding a derivative is actually useful. Okay, it allows us to find physical, you know, variables to speed from a distance time graph. That's one of the uses. But there's also many uses as well of derivatives that we will see later in this tutorial or in further tutorials. And now let's talk about the rules of differentiation, actually, or how does it work for different functions. Let's have a look here. Yeah. Okay, so for differentiation, actually, let's say if we're dealing with a polynomial, okay, let's say a polynomial function, how are we going to differentiate a polynomial function? Is, let's say we're given a simple function in terms of fx as, maybe we have it as ax to the power of n plus bx to the power of n minus 1 plus cx to the power of n minus 2 all the way until maybe f, for example, no, f, okay, let's just put d, until d, okay, let's just put it that way, d. So d, where basically x equals to n minus n, right, and this would be equivalent to 0, right, x to the power of 0, which obviously would mean 1, right, so it becomes a constant. So in this case, how do we differentiate polynomial is when we try to differentiate polynomial, and remember that in order to differentiate, sometimes you write it like this as dfx over dx, meaning taking the derivative of f at x itself, or we write it as f prime x, which means the same thing. It'll simply be n a x to the power of n minus 1. So what we did here is that let me run in blue here. We actually took the n, we shifted it to this side, right? We brought it down right here, and the power we minused it with 1. Okay, and a is a constant itself, so this is unaffected, so this is a constant, right? So it's not affected at all. Okay, so therefore we leave it as it is. And likewise, as we follow suit, so we'd obviously have here n minus 1 times b x to the power of n minus 1 minus 1 would be 2. And then you get the gist basically. So you'll have your n minus 2 c x to the power of n minus 3, and you'll keep going on. But if you have a constant d, right, normally it will not be considered and we'll have it as a 0. Okay, so basically that's the idea on how to differentiate for polynomials. Okay, for trig functions and exponents and hyperbolic functions, later functions we'll discuss in other tutorials. So other functions in other tutorials. All right, so other functions in later tutorials, later vids. Okay, so we're going to discuss them in later videos. All right, so we don't talk about them right now. Okay, now we're going to talk about the rules. Actually, we're going to talk a little bit about the rules of differentiation. There are some rules actually that we have to follow, and for now we'll just focus on 2 rules, like 2 simple rules. So let's go to rule 1. Okay, oops, sorry. Okay, so we have some rules. Let me put that yellow, my bad. Rules. Okay, so the first rule is what we call as the constant rule. Okay, it's very straightforward, meaning to say that, let's say we have a function, right, written like this: y equals to ax to the power of 5. So when we do the differentiation, right, so when you do differentiation, so take dy dx, okay, and we would have the a, right, times dy dx x to the power of 5. Okay, of course the a also will be differentiated as well, but the a can be taken out anyway because it's a constant, so it will not be differentiated in this case. So my apologies, it will be here x to the power of 4, right, times 5. Let me write that nicely, by the way, to be clear. So you have the 5 outside and you have x to the power of 4, so it would be 5a x to the power of 4. So this is what we call as the constant rule, meaning to say that if you have a constant, actually, right, if we have a constant right here, that's a, that's outside the function that you're differentiating, in this case is x, the a will remain untouched, so it will not be touched at all. It will be untouched. Okay, so it will be untouched. Alright, so that's the first rule. It's a very basic rule, by the way, very simple rule. Okay, and the second rule, okay, oops, let me write that in yellow. Okay, the second rule is that, let's say you have a function like this. Okay, so y equals to maybe x to the power of 5 times with let's see, 2x to the power of 4. For example, let's say you're given a function like this. Okay, and how do you find the derivative? How do I find the dy dx in this case, right? How do I find it? Okay, so one way to do it is to split into 2 parts. Okay, we're gonna split this x to the power of 5 into a part known as u, and the 2x to the power of 4 in the part known as v. Okay, so what we're gonna do is we're gonna have a function of u as x to the power of 5. Therefore we're gonna differentiate it, which would take the du dx, and this will become 5x to the power of 4 And for v, we will have a function right here, which is 2x to the power of 4, and dv dx is quite simply 2 times 4 x to the power of 3, which will obviously give me 8x cubed. Okay, so once we have got that, what is our next step? Okay, let me were to erase this real quick. Let me just erase this part. Okay, so I'm going to erase the first rule, by the way, because I think we already know what the first rule is. Alright, is that we're going to write it like this. Okay, so we're going to write it as dy dx. Okay, so dy dx is equals to v du dx plus u dv dx. Okay, so this rule, okay, what I just wrote right here, is called the product rule. Okay, it's called the product rule. Right, this is the second most important rule they have to remember. And if you want to write it properly, right, so in this case it would be dy dx is just equivalent to v, in our case, is 2x to the power of 4 multiply with du dx is 5x to the power of 4 plus u is x to the power of 5 and dv dx is 8x cubed. And of course, if you were to simplify this, it will just simply become 2 times 5 will be 10 x to the power of 8 plus 8 x to the power of 8, right, which would have obviously given us 18 x to the power of 8, right? So that's the answer itself, actually, dy dx. And if you also do it normally as well, so you can simplify as y equals to 2x to the power of 9. Therefore your dy dx, if you use a normal method, is just simply 2 times 9 will become 18 x to the power of 8. Okay, so you can see that whether you do the normal method or whether you use the product rule, both cases are correct. Normally we use product rule, let's say if we're dealing with other functions, okay, which of course I will reserve for the other tutorials. So now that's rule 2 covered. So let's go to rule number 3. Okay, we'll go to rule number 3 actually. Okay. So rule number 3, okay, is let's say you have a function like this. So y equals to 2x squared minus 1 over 5x to the power of 4. And the question asks you to obviously find the dy dx. How are you going to do that? Okay, just like before, we'll take two parts. Okay, we're going to denote the numerator as u and we're going to denote the denominator as v. So it will be u is equals to 2x squared minus 1 and v is equals to 5x to the power of 4. So therefore du dx would become, we differentiate it, would be 4x, and minus 1 we differentiate respect to x will become 0, so it will obviously become like plus 0, so we'll just leave it as 4x. Whereas if we take the dv dx, okay, of course we're going to bring the 4 to that side, right, and we would end up having as 20 x to the power of 3, right, because 4 minus 1 is 3. Okay, so when we try to find the dy dx, okay, simply it is just v du dx minus u dv dx over v squared. So this rule is what we call as the quotient rule. Okay, this is what we call as the quotient rule, right? So how do we solve this? Is that we of course substitute the values we got earlier, so it's just simply v 5x to the power 4, du dx is 4x minus u, right, which is 2x squared minus 1, and dv dx is 20x cubed, and it's over v square, okay, which is obviously 5x to the power 4 squared. And of course you can simplify this and try to get the simplest answer possible, but I'm just gonna leave it right here just to actually show you this is how we do the quotient rule. Okay, and we also have some other rules too as well, which I also discuss as well. So let's erase this. Okay, so I believe this is rule number 4 now. We're in rule number 4. So let's say you are given a function, okay, where you have a function of y. So y is expressed as u square plus 2, and you have another function of u expressed in terms of x, which is obviously u equals to x cubed plus 4x squared plus x. Okay, so now we're given two functions. All right, we have a function of y represented in terms of u, and we have a function of u represented in terms of x. Right, you can see represented in terms of x right away. So now if we are asked to find what is dy dx, how are you going to find it? Okay, so what we do first is that first we find this dy du. Okay, so first of all we'll find, I'll draw an arrow right here, find dy du. Okay, so how do we find dy du? Is very simple. So if we take the derivative of y respect to u, we know it's gonna be just 2u, right? Because the 2 will obviously be cancelled off, it'll be 0, right? And when the next thing we're gonna do, and I'm gonna put it in green, maybe green as well, is to find du dx. Okay, need to find du dx. Again, it's very simple. So it would be du dx is equals to what? 3x squared plus 8x plus 1. Okay, so once we've already found it out, so what do we do actually? What do I do with this dy du and du dx? So I'm going to multiply them together. Okay, so dy dx is just equivalent to, oh my god, sorry, dy du times du dx. Okay, and this is quite a logical way to multiply because you can easily cancel out the du terms, right? Then of course we'll get dy dx. That's why we actually multiply in the first place. And since we know dy du is just simply 2u times with 3x squared plus 8x plus 1, and then we substitute this u right away, right? This u here with this relationship between u and x, right? So it would be simply 2x cubed plus 4x squared plus x times 3x squared plus 8x plus 1. So this is our derivative, this is our dy dx. So this rule that we've did here just now is what is called as the chain rule. Okay, is what we call as the chain rule itself. Alright, so basically why is it called a chain rule? Is because you're actually multiplying two derivatives together to get your desired derivative. Dy times du multiply du times dx, and this is we get dy dx. Okay, so that's the rule number 4. I believe there is one more rule left. Actually, there is one last rule that we could mention actually, right, before we proceed on, and that is the inverse rule. Okay, I'm gonna have to erase this real quick. Okay. Okay. So the last rule here we're going to mention, right, before we move on, is the inverse rule, meaning to say that if there is a function, so if y is equals to the inverse function of x, and x can be expressed as a function of y, okay, so what it means is that dy dx, okay, dy dx in this case would be 1 over dx dy. Okay, so 1 over dx dy, alright, is equals to dy dx. So yeah, I think that should be the right way of doing it. Let me just have a look first. Alright, let me just check real quick. Yep, this is 1 over dx dy. Okay, so let's give an example. Let's just say, for instance, that I have a function here that x is equals to 2y. Okay, so of course your dx dy would be 2, right? So if I were to inverse this function, right, that means y would be equals to half x. Okay, and when we do the differentiative, so dy over dx is equals to half, and it actually follows this particular rule about inverse functions, because if you want to find the dy dx, we could just say it's just 1 over dx dy, and since our dx dy is 2, so it just becomes 1 over 2. So you see, it does follow the rule actually. Okay, so this is actually a very neat trick if you're dealing with inverse functions. So yeah, hopefully that's clear. I think that's about the rules here on differentiation. Okay, so without further ado, we're gonna do some exercises right now. So yeah, let's look at some simple examples. Let's see. Okay, so here's one example. We're asked to differentiate. Okay, oops, let me write down real nicely. Right, yeah, okay. We're asked to differentiate. Okay, we're asked to differentiate this particular function, right? So differentiate fx is equivalent to 1 over 3x cubed. Okay, so how are we going to differentiate this? Okay, remember the tip that for, if let's say you have a case where the indices is like this, like let's say for example m is your normal number and you have it to the power of n, is equivalent to m to the power of negative n. Okay, so this is a tip I'll give you. So I suggest you guys to do pause the video and give it a try. It's pretty simple, but do pause and give it a try. Okay, assuming that you've paused it and give it a try, let's just go and straight to the answer. So in this case, that would be what? So as I said before, so you write it as 1 over 3x to the power of negative 3 to make your life simpler. Then of course f prime x would be negative 3, 1 over 3 times 1 over 3, x to the power of negative 3 minus 1 becomes negative 4. So of course negative 3 and negative 3 will cancel out. Let me use a different color to cancel out. orange. Okay, so cancel that out. Be 1. So therefore you would end up having negative x to the power of negative 4, which is equals to negative 1 over x4. Okay, right, so that was pretty straightforward. Now let's go for a slightly interesting question. Let me erase this real quick. Okay, so we have a function here. Okay, so differentiate so you have a function right here that's given to us. Okay, so it become root x minus 1 okay over root x. I think this 1 over root x multiply with x minus 1 over root x. Okay, so I'll give you guys some time also actually to, pause the video and try to solve the question. And here's a tip. Let's say you have root x, it means what? It means x to the power of half. Okay, so yeah. Okay, assuming you guys have paused the video and give it a try, so let's try to solve it ourselves. So first and foremost, even though it looks a little tricky, I would suggest to try to multiply all the terms actually to make it easier for yourself. Well, let's start real quick. So we would have here root x times x becomes x root x. Okay, and when you have your root x multiply with negative 1 over root x, it just becomes minus 1. Pretty straightforward. And you have your minus x over root x, so x over root x. Okay, and you'd have your plus, so become 1 over x. Okay, so we can further simplify this problem. So we'll end up having here x times x to the power of half, right, minus 1 minus x over x to the power of half plus x to the power of negative 1. Remember that if it's on the bottom, when you bring it up to the top, it becomes to a negative, negative indices. So of course we plus them together, so we get your x to the power of 3 over 2 minus 1 minus x to the power of half plus x to the power of negative 1. Okay, so once you do the derivative of it, it's gonna become 3 over 2 x to the power of 3 over 2 minus 1 would be half, and this 1 would be 0, so it becomes, and this one will become half x to the power of negative half, right, because 1 minus half minus 1 become negative half, minus x to the power of negative 2. And if you want to further simplify it, it just becomes 3 over 2 root x minus 1 over 2 root x minus 1 over x squared. So yeah, this is basically your final answer when you do the differentiation. Okay, and that's just a normal way of doing it. But let's say for instance you want to use the product rule, okay, because we talked about the product rule earlier. Okay, so in this case let's use the product rule. Let me make this a bit smaller. Okay, so let's say if we're trying to solve this with the product rule. Okay, let me choose pen here, choose a different color. Okay, so of course I'm going to denote it as view and I'm going to denote it as v. Okay, so for u, it'll be what? It's just simply root x minus 1 over root x. Okay, so this is root x minus 1 over root x, which we can write it simply as x to the power of half minus x to the power of negative half, right? Thus du dx would be half x to the power of negative half plus half x to the power of negative 3 over 2. Okay, then for v, is it just simply x minus 1 over root x, which we can of course be rewritten as x minus x to the power of negative half. Then dv dx would be x will become 1 plus half x to the power of negative 3 over 2. Okay, so now we try to find the f prime x, right, which is basically using the product rule. It's quite straightforward. It's just simply v du dx plus u dv dx. Okay, so this is the product rule that we've been talking about earlier. Okay, so in this case this would be x minus x to the power of negative half. Du dx is half x to the power of negative half plus half x to the power of negative 3 over 2. Okay, plus u would be x to the power of half minus x to the power of negative half, multiply with dv dx will become 1 plus 1 over 2 x to the power of negative 3 over 2. Okay, so we can leave it like this actually with product rule, because the question didn't ask us to simplify anything. It's just a way to do a product rule. Okay, so yeah, that's basically how we solve this question with product rule. Okay, let's say we need to solve a product rule. Okay, so now we go one last question, right, before we can end this tutorial session. Make this eraser bigger. Okay, so one last question a day. All right, so we're given a function, okay, which is written like this supposedly. Okay, so differentiate this function right here. So it's fx, oops, sorry, differentiate fx is equals to x to the power of 2 over 3 over x over 1 over 3 to the power of 1 over 3 plus 1. Okay, so I'll give you guys the opportunity to pause the video and give it yourself a shot. Alright, okay, so assuming you guys have paused the video and attempted to try it out, so what we can actually see here is that this question, right, it's written in the form of fraction. So the only way we could solve this easily is through quotient rule. So I'll take it in terms of u and in terms of v. So you can see that u is just simply x to the power of 2/3. So therefore du dx would be 2/3 x to the power of 2/3 minus 1, which would give me negative 1 over 3. And then for v, it's just simply x to the power of 1/3 plus 1. So dv dx would be 1/3 x to the power of 1/3 minus 1 would give me negative 2/3. Okay, and this plus 1 will not be counted, by the way, so yeah, we don't really care about it. So quotient rule, it states that if we are finding the f prime x, okay, we're finding the f prime x, it's just simply v du dx minus u dv dx over v squared. So in this case, it is just simply x to the power 1/3 plus 1. Du dx is 2/3 x to the power negative 1/3. Okay, minus u, which is just x to the power of 2/3. Okay, and dv dx is 1/3 x to the power of negative 2/3. Okay, over v squared, which would be in this case x to the power of 1/3 plus 1 squared. Alright, so you can leave it like this. Actually, you don't really have to simplify it. So whoops. So yeah, that's basically how you do for quotient rule. So that'll be the end for today's tutorial session, or tutorial video actually. And of course, for the other rules like the chain rule, right? The chain rule and chain rule. We also had the inverse rule. We talked about it. Okay. Of course, there'll be other videos following along for these rules. Okay. And of course, we'll be discussing more about other functions, right? Some other functions to differentiate besides polynomials and other indices function, right? For example, where we had square root of x, which you can write as x to the power of half, or 1 over x squared, whatever x squared, which is obviously just equals to x to the power of negative 2. We've only discussed up to this range so far. We haven't discussed other functions, for instance, which we'll discuss in the next video, like for example trig, right? Trig, exponents, log, and also we have hyperbolic functions as well. Okay, so yeah, I think that's about it. So thank you so much for watching today's video, and hopefully this helps. See you next time.